Okay, imagine a broken cosmic sprinkler floating out in the pitch-black darkness of deep space. It's blasting out wild jets of gas and ice, and it's spinning faster and faster until the forces acting on it become so incredibly violent that it does the unthinkable. It literally stops dead in its tracks and then starts spinning completely backward. I know, it sounds exactly like science fiction, right? But this isn't fiction. This is real. This is happening right now to a comet in our very own solar system. It's all detailed in a fascinating newly published paper in the Astronomical Journal titled Reversal of Spin, Comet 41P/Tuttle Giacobini Kresak by UCLA's David Jewett. So, welcome to today's explainer. We're going to unpack one of the absolute most bizarre phenomenons recently observed in space, and we'll see how it completely rewrites our understanding of just how long these icy rocks actually live.
So, the ultimate mystery we're trying to solve today is this. Can a comet really spin so fast that it forces itself to reverse its own rotation? I mean, we usually think of celestial bodies as these majestic, highly stable objects just coasting along, guided by the steady hand of gravity. But out in the cold vacuum of space, things can get incredibly chaotic. We're going to treat this explainer like a breaking news investigation today, piecing together all these little clues from deep space to answer that exact question. Because what David Jewett discovered here, it isn't just some minor, quirky astronomical anomaly. It's a dramatic, high-stakes story of a dying world that is quite literally tearing itself apart. And it matters because it fundamentally changes how we view the volatile history of our solar system. It shows us exactly what happens when small, fragile bodies are pushed to their absolute physical limits. So, let's go ahead and meet our suspect. All right. Meet Jupiter Family Comet 41P, or as we're just going to call it today to save time, TGK. Now, back in early 2017, as TGK was making its closest approach to the Sun, astronomers noticed a really massive problem. The comet's rotation period, the time it takes to complete one full spin, mysteriously more than doubled in just 2 short months. It went from spinning once every 20 hours to once every 53 hours. It was rapidly slamming on the brakes. But why? Well, to figure that out, the researcher had to do some really serious cosmic detective work. Jewett didn't just point a telescope at the sky and hope for the best. He actually dug into stacked archival images from the Hubble Space Telescope that were taken way back in December 2017, which was about 8 months after the comet passed the Sun. By isolating the comet's incredibly faint glow from all the background stars, he was able to calculate some vital statistics about our suspect. And boom, here is our first massive clue, 500. That's the effective radius of comet TGK, in meters. It is tiny. We're talking just half a kilometer across. To put that into perspective, you could easily just walk across this entire comet in a few minutes. And because it's so incredibly small, it barely has any mass. This diminutive size makes it highly susceptible to being pushed around by external forces. Honestly, it's like a feather caught in a windstorm. Which brings us perfectly to the actual mechanism at play here. Outgassing torque. Let's just break that down into plain English. As the comet gets super close to the Sun, the ice on its surface heats up and violently turns into gas, shooting out into space like little jets. But because the comet is in a perfectly smooth, round sphere, these jets shoot out totally unevenly. Think of a deflating balloon zooming wildly around your living room, or that broken lawn sprinkler we talked about earlier. These uneven jets act exactly like thrusters, forcing this tiny 500-meter rock into a wild, totally uncontrollable spin. Now, how do we know this for sure? The proof of this chaotic movement is right here in the data. It's called a phase dispersion parameter plot, which I know sounds super complicated, but you can really just think of it as the comet's jagged heartbeat. By analyzing the fluctuations in the comet's brightness over time in those Hubble images, this graph proves that by December 2017, the comet was rotating once every 14.4 hours. Remember, earlier in the year, it had slowed way down to 53 hours, and now it's suddenly back to 14.4. Something drastically changed. So we're basically faced with 2 possibilities, kind of like a detective crossing out theories on a whiteboard. Did the outgassing jets suddenly magically reverse their push and speed the comet back up in the exact same direction? Or did the comet slow down completely to zero and then start spinning backward? Now, there are a few gaps in the data simply because we can't watch it 24/7. But the mathematical modeling, specifically the very smooth deceleration curve calculated by the researcher, strongly points to the second option. The torque was so strong and the comet was so incredibly small that it likely hit zero in June 2017 and completely reversed its spin. And this mathematical twist builds into a really high-stakes reality. We're looking at a huge disparity here. 1,500 years versus a few decades.
The forces twisting this comet back and forth are violently stressing its structural integrity. The calculations show that this rapid spin-up is going to literally tear the comet apart. While it has a highly stable orbital lifespan of about 1,500 years, meaning its path around the sun isn't going to change anytime soon, its actual physical lifespan before it shatters into a million pieces is shockingly short. We're talking maybe just a few decades left. And looking at the timeline really puts this all into perspective for us. TJK was injected into its current orbit around 500 AD. That is right around the fall of the Roman Empire. It survived all that time, but then we hit 2017. The spin slows down in the spring, it likely hits zero by June, and by December it is fully spinning backward. If this volatile torque continues, the centrifugal forces are going to completely overcome the comet's gravity. By the 2040s, or maybe even sooner, rotational breakup is basically imminent. It's going to shatter. Which naturally leads the researcher to pose a very honest, very pressing question. Why is TGK still here at all? If its physical clock is ticking so insanely fast, just 13 to 25 years until total destruction, how on earth did it survive the last 1,500 years? Well, the paper offers two really fascinating possibilities. First, maybe the comet is just having an unusually hyperactive decade, and normally it's much quieter and safer. Or second, perhaps TGK used to be a massive, kilometer-scale world that has been slowly whittled down over the centuries, and what we are watching right now is just the final, dying remnant of that much larger body. And honestly, we just don't have the final answer to that yet, which brings us to the ultimate cliffhanger. Will comet TJK even survive its next close pass by the sun in 2028? This research shows us that the solar system isn't just some static museum of rocks. It's a dynamic and, honestly, sometimes violent place where tiny worlds are literally spun to death by the heat of the sun. In 2028, astronomers are going to be watching very, very closely, and we might just have a front row seat to the final days of this bizarre, backward-spinning comet. Thank you so much for joining me for this explainer, and as always, keep looking up.